Hello everyone, I'm Dongming Luan, and I'm honored to attend SCPP 2021. The title of my paper is Distributed Game Theoretical Route Navigation for Vehicular Crowdsensing. The authors of this paper are N. Wang, Dongming Luan, Yongjian Yang, Zihe Wang, Pengmin Dong, Dawei Li, Wenbin Liu, and Jie Wu. I will introduce the paper from the following 7 parts. Firstly, I will introduce the motivation. With the proliferation of mobile devices, mobile crowdsensing has attracted much attention. It utilizes the mobile users to move to the specific location to perform the sensing tasks. Then, they upload the sensing results to the platform. The platform processes the upload data and provides crowdsensing services, such as traffic monitoring and noise monitoring. Vehicular crowdsensing is a special case of mobile crowdsensing. It takes advantage of the mobility of vehicles to perform the sensing tasks in large areas. In vehicular crowdsensing, the platform needs to assign the tasks to the users. It leads to the task allocation problem. The existing centralized task allocation strategies has a heavy computation complexity, and the centralized task allocation may fail to satisfy all the users with the allocation results. For example, a user may be unwilling to deviate from the daily route to perform a remote task. Considering the drivers usually utilize the map navigation systems, we are inspired to consider a distributed task allocation with the help of the route navigation. As shown in the left part, there are 3 mobile users. When the users input the origin and the destinations in their smartphones, several routes are recommended to them. Each route may cover some emphasized tasks with a reward. When a user selects a route, it can complete the tasks on this route and get the corresponding task rewards. In this way, the users select routes to perform tasks in a distributed manner, but it remains unclear how to get users to select the suitable routes in order to maximize the user's profits, especially when the reward of each task is equally shared by the selected users. The route selections of users may influence each other in this scenario, as shown in the right part. An intuitive approach for each user is to select the route with the maximum reward. However, this leads to the least total reward, because users need to share the reward of their overlapped tasks. An ideal approach is centralized optimal. It achieves the highest total reward, but it does not reach an equilibrium state because the third user can select the fourth route to get more profit. Our target solution is distributed equilibrium. It achieves the trade-off where a relatively high reward and an equilibrium state are achieved. In this situation, no user has the incentive to change the decision to get more profit unilaterally. So, the problem in this paper is how to design a distributed route navigation approach to reach an equilibrium state while guaranteeing a good profit performance. There are 3 challenges. The first is how to construct a distributed model to achieve the equilibrium while guaranteeing the profit performance. The second is malware. During the route navigation process, each user has an individual preference. For example, some users may want high task rewards, while others may want to select routes with low detour distance and congestion level. Similarly, the platform also has a specific task allocation purpose, such as maximizing task coverage. So the second challenge is how to design a unified distributed algorithm that considering the requirements of both the platform and users. Finally, even if we find the distributed equilibrium state, the profit performance is not always optimal. So the third challenge is how to guarantee a lower performance bound with respect to the centralized optimal solution. The profit function is as follows. The first part is the reward that the user received after performing the tasks on the selected route. The reward of each task is equally shared by the selected user. The second part is the cost incurred by traveling the detour distance, and the HSI is the detour distance. The third part is the cost incurred by the congestion on the route. The parameter alpha I, beta I, gamma I is are the user parameters for user I. The users can adjust them to satisfy their preference. Similarly, the platform can adjust the system parameters to achieve their different purpose. There is a simple example of the influence of phi and theta. The platform can decrease the values of both phi and theta to maximize the number of tasks covered by users. And by increasing the values of phi, the platform can guide users to select the routes with short detour distance. And the platform can guide users to select the routes with low congestion level by increasing the value of theta. We further prove the NP-hardness of the centralized problem. It shows the complexity of the centralized problem. So we design a distributed algorithm with a low computation complexity. Then I will introduce the two definitions. Firstly, I introduce the Nash equilibrium. In Nash equilibrium, no user can improve the profit by changing the strategy unilaterally. And the potential game has two important properties. First, there always exists at least one Nash equilibrium in a potential game, and the potential game always converges to a Nash equilibrium in a finite number of decision steps. We prove the multi-user route navigation game as a weighted potential game, so it can converge to a Nash equilibrium in a finite number of decision steps. Furthermore, we design a distributed route navigation strategy for the user. It first initializes the user parameters and selects a route from the recommended route size. Then, in each decision slot, each user calculates the best route site. The best route site is defined as the set of route decisions that maximize the profit of the user and can improve the profit compared to the previous decision slot. Then the user sends a request to the platform for updating the decision. If the user wins the opportunity, it changes the decision, otherwise it remains the decision unchanged. The algorithm is terminated when all the users receive the termination message. For the platform, firstly, it sends the parameters and information to the users. Then, the platform selects a user to update the decision. When no request is received from the users, the platform sends the termination message to all the users. In their proposed strategies, most of the computation load is distributed to the users. Each user calculates the profit and makes the decision locally to maximize a local profit. The platform cannot control users. It merely selects a random user to update the decision and transmit the information among users. We conduct simulations based on three real-world datasets. Figure 3 shows the dynamics of the profits of 15 users. It is obvious that the profit of the user changes with the decision updates in the beginning and can converge to a stable point. Figure 6 shows the value of the potential function and the total profits of all users can converge to an equilibrium state. The above simulation results verify the convergence for Nash equilibrium. These two figures show that the proposed algorithm achieves the best coverage and average reward compared to the baseline methods. We test the influence of adjusting the system parameters and user parameters. The simulation results show that the users and the platform can achieve different purposes by adjusting the parameters. Thanks for listening. If you have any question, I'm happy to answer it. Thank you very much.